All right, there we go. Okay, so once again, guys, you will notice the domain is all positive integers. However, the range doesn't necessarily have to be just integers. You can end up with fractions. Now, at some point, we talked about this type of function, guys. Does anybody remember what kind of function that is called? Anybody? No? Mm-hmm.
Rational.
A rational function. Very good. So guys, if we were to go ahead and sketch the graph of this rational function, now because the domain is restricted to all values greater than 0, when we graph it, the graph would look something like this. And as x approaches, that's supposed to be just one line here, okay? So as x approaches positive infinity, what is the value of the function approaching? And that's supposed to be on n, guys, okay? So what is f of n approaching as the value of n are increasing? So in other words, on the previous part of the problem, guys, I plugged in 1, I got 1. Let's say 1 is located right here. I plugged in 1, I got 1. I plugged in 2, I got 1/2. I plugged in 3, I got 1/8. I plugged in 4. Did I do 4? No, I didn't do 4. If n is equal to 4, f of 4 will equal to 1/4. So when I plug in 4, I get 1/4. Okay, and so forth and so on. So as the n values are approaching positive infinity, they're increasing from left to right. What seems to be happening with the function? The function is approaching 0. By the way, these type of functions, guys, when we get to calculus, we're going to be talking about limits. So this is a precursor to limits as well, all right? So what is the bottom line, guys? A sequence is basically a function. So you've seen these before. Now, the terms that we talk about, we could also use subscripts to represent the terms. We could use the letter A to represent the terms, and we could use subscripts to indicate which term we're looking for. For example, a sub 1 was equal to 1. This right here represents the first term in the sequence. Now, the next term we found was when n was equal to 2, and when we plugged in that 2, we got 1/2. So this would represent the second term. And then, of course, the list goes on and on. A sub 3 would represent 1/3. So then this would represent your third term in the sequence. So if we were to write it out, the sequence itself would look like this. 1, that's the first term. 1/2 is the second term. 1/3 is the third term. Then 1/4, 1/5, and then of course you use your ellipsis to show that this term continues all the way up to infinity. Any questions about this, guys? No questions? All right, so now let's keep going. Let's say I were to give you this particular function right here. Let me find a good one for you. Let's see here. Ooh, that one's too easy. Okay, here's one. A sub n is equal to, that looks like an m, but that's actually an n. Okay, let's try it one more time. A sub n is equal to a1 plus, n minus 1 times 3, okay? So this represents a sequence. You could also refer to this as a function, okay? So we could also rewrite this as a1 plus n minus 1 times 3. All right, guys. So now we want to go ahead and figure out the terms in the sequence. We're going to list the first 5 terms of the sequence. Okay. Now, for this one right here, if we start out with the first term, we'd have A1 is equal to, let's see here, 1 minus 1 times 3. 1 minus 1 is 0. So the first term would just be A1. Now, if we were to go to the second term, the second term would be A1 plus 2 minus 1 times 3, which would end up giving us A1 plus 3. So the next term would be the first term plus 3. Now, let's go to the third term. We do A1 plus 3 minus 1 times 3. And so this one will equal out to A1 plus 6. So the third term would be A1 plus 6. Now, do you guys see a pattern starting to form? Can you oh, yes. Okay, I didn't see her there. There we go, Stacy. Okay, thank you. That was Lee. Okay, guys. So guys, do you see a pattern forming here? We got A1, that's the first term. A1 plus 3 is the second term. A1 plus 6 is the third term. So what would be the fourth term? A1 plus, anybody? Plus 9, very good. And then the fifth term would be A1 plus, what's the next one? Plus, anybody? Ooh, 4 minus, no, give me the number 12 page. Very good, 12. Okay, so what I want you guys to notice is that you figured out a pattern. There's a pattern here. We're going from 3 to 6 to 9 and then to a 12. There's a pattern here, okay? So sometimes these sequences, they may be a pattern. And so when we talk about a pattern, guys, there could be two types of patterns you find. You could find an arithmetic pattern, and we're going to be talking about this. And the arithmetic pattern or arithmetic sequence series is coming up too, is one where you are getting each term by adding or subtracting the same thing over and over again. There is also a geometric pattern, and the geometric pattern has to do with either multiplication or division. So these are the two types of patterns you're going to encounter when you guys are working with sequences. Now, additionally, okay, sometimes they just give you a pattern. Here's a pattern. Figure out what we're adding, multiplying, or dividing to each term to get to the next one. So guys, here's a quick one. Let's say we have this sequence here. 1, 4, 9, 16, 25. The question is first, what is the pattern? What are they doing to each term to get to the next one, okay? Now, this one has two possibilities, by the way, okay? So how are they getting from 1 to 4? How are they getting from 1 to 4, from 4 to 9, from 9 to 16, from 16 to 25? How are they doing it? What are they doing? And once you figure out the pattern, then you are able to figure out the next term as well as the term after that. So they might ask you, what are the next two terms? All right, guys. So let's see if some of you can figure out the pattern. What is the pattern here? Anybody? No one? Okay, take a guess, guys. Take a guess at what you think the pattern is. No? Take a guess. All right, nobody's taking a guess. All right. So
Geometric.
Yes, there is a geometric pattern. Okay, but what is that pattern to get to the next term? What are you adding?
Would it be an square?
Huh?
Would it be an square?
Okay, so you're taking each term and you're squaring it. So something like this, n to the second power, where n is the first, n starts at 1. So the first term here would be n equals to 1. And if n equals to 1, 1 squared will give you 1. If n equals to 2, 2 squared gives you 4, and so forth and so on. Okay, that's a good one. Does anybody else see another pattern? Because there's a possibility of another pattern. Anybody? Okay, how about this, guys? 1 plus 3. The first term is 1. But if you add 3 to the first term, you get 4. All right. Now, if you take 4, you add 5 to it, that gives you 9. And if you take the 9, you add 7 to it, that gives you 16. Isn't that the same pattern? Do you guys see it? No? Okay, some of you are not seeing it. All right, so we'll go with the basic one. So this one right here represents a pattern. So once you figure out the pattern, guys, you can go ahead and use it to figure out the next 2 terms in the sequence. So then what would be the answer for the next 2 terms in the sequence? What would be the next one after 25? That one would be 36. And so the next one after that would be 49. Very good. Now, earlier, Lee said, oh, this is a geometric pattern. Now, how do we know it's a geometric pattern? Because we are multiplying. Any pattern involving multiplication has to do with a geometric pattern. Now, if you can take a pattern, guys, and you formulate it into a formula, if you can take a pattern and create a formula for it, these type of problems, we call them a recursive formula. Recursive formula. So if you can take a pattern and create a formula for it, like the n squared we just finished talking about, we call this formula a recursive pattern, where each term in the sequence, when we talk about a recursive pattern, it is a pattern where each term in the sequence depends or it relies on the previous terms. Depends on the value of the previous term, guys. So these are the types of problems we are going to be looking at in this particular chapter. Now, let me go ahead and start with something very easy. Let's see here. Let's find a really good little pattern. Okay. Here's one. S sub n is equal to n squared plus 1. And they want you to write down the first 5 terms of this one, guys. Okay? So if they want you to write the first 5 terms, you would start out with S sub 1. Take the 1, plug it in for n, work it out. So this one would give you 2. Then you go to S sub 2. S sub 2 will be 2 squared, and 2 squared plus 1 will give you 5, and so forth and so on. I'm going to go to S sub 3. S sub 3 will be 3 squared plus 1, which gives you 10. So I've got the first term, which is 2, the second term, which is 5, the third term is 10. Now, what's the next term after 10, guys? What would the next term be? Anybody? Okay, the next term, you would take 4 and plug it in. 4 squared is 16. 16 plus 1 gives you 17. Very good. And then what's the one after 17, guys? The next one would be? What's the next one? 26. Very good. Now, additionally, guys, one of the things we're going to be seeing in this particular chapter are the factorials, okay? Now, when we talk about a factorial, the symbol we use is this right here, the exclamation point. Give me a thumbs up if you've seen a factorial before. Give me a thumbs up if you've seen this symbol and you know what a factorial is. Gabrielle, Leslie. Oh, that's awesome. Kirsten. Okay, perfect. Guys, when we talk about a factorial, it looks something like this, n factorial. N factorial means you're going to multiply n by each of its preceding values. You're going to take n and multiply it by each of its preceding values until you get to 1. So, for example, if you had 5 factorial, okay? By the way, we use this quite often in statistics, the fundamental counting principle. When we're doing permutations and combinations, that's going to be talked about very quickly in this class too, okay? So if we had 5 factorial, we would take 5 and multiply it by all of its preceding values. So in this case, we multiply it by 4, multiply it by 3, multiply it by 2, and multiply it by 1. Now, when you multiply all of this together, guys, 5 times 4 is 20. 20 times 6 gives you 120. So that's what 5 factorial would simplify to, 120. Now, what do we put the terms in once we find them? What do we put the terms in once we find them? Okay. Are we talking about the terms of the sequence? Okay, remember it's a pattern. So the previous one we just looked at, I just listed out the terms for you. 2, 4, what was the other one? I think it was 10, 17, 26. And of course, these sequences, for now, they keep going to infinity. Now, remember guys, be careful with these sequences. Not all sequences are infinite. Some of them may be finite sequences, and we're going to talk about them later on in the week, okay? So yes, Paige, when you write out your numbers, just write it out as a list, separated with a comma, and I use the ellipsis here to show that the sequence continues up to positive infinity, all right? So it's the same thing as the domain of a function. The domain of the function represents all values greater than 0. And so the range of this function would represent all values up to positive infinity. Now, for this one right here, when we go to the range, we're looking at f of n. Actually, we just use s sub n for that one, would be greater than 0. So it keeps going on and on and on and on. So when you write it out, just write it out as a list. Okay, Paige? You're good? Yes, 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 yes. All right, guys. So let's get to some nitty-gritty of this, okay? One of the most important sequences or most recognized sequences, I'm trying to spell this correctly, is the Fibonacci sequence, the Fibonacci sequence. Now, give me a thumbs up if you've seen the Fibonacci sequence before, guys. Anybody? Oh, nobody's seen the Fibonacci sequence. Okay, this is going to come along later on too when we start talking about binomial expansion. So for the Fibonacci sequence, guys, this is where they give you the first few terms. And then using a formula, you can use the previous terms to get to the next set of terms in the sequence. So for the Fibonacci sequence, they give you the first one. A1 is equal to 1. A2 is also equal to 1. Now, A2, on the other hand, is equal to 2. A3 is equal to, no, that was A3. A4 is equal to 3. And then A5 is equal to 5. Now, the question is, how are we coming up with this? So they give you the first one, they give you the second one. The formula we use for this, guys, to calculate any term, and we could call this the general term formula, is this one right here. AN is equal to A times, A sub n minus 2 plus A times n sub n minus 1. Now, what in the world am I talking about? So on this one right here, if we're looking at the third term, look at what happens. If you have the first term, you have the second term. Here's the third term, guys. Here's how you would write it out. So wherever you find an n, plug in that 3, plug in that 3. Wherever you find an n, plug in that 3, okay? So what does this represent? This represents A1 plus A2. Now, what is the value of A1? It is 1. What is the value of A2? It is also 1. So when you add them together, what do you end up with? You end up with 2. I'm trying to move this. Ooh, hold on, guys. Okay. All right, I'm running out of room down here. All right, I'm gonna have to erase some of this. So let me erase some of this, guys. So let me go back up here and erase some of this. Okay, because I don't need this part right here. All right, guys. So I'm gonna rewrite it. So the A sub 3 is equal to A sub 3 minus 2 plus A sub 3 minus 1, okay? Now, A sub 3 minus 2 would represent A1, and then A sub 3 minus 1 would represent A2. Now, what is the value of A1? It's 1. What is the value of A2? 1. When you add them together, you get 2. So that's how we're figuring out the third term. So basically, the value of the third term is found by using the value of the previous term. So if we were to go to the fourth term, we get A sub 4 minus 2 plus A sub 4 minus 1. So eventually you will notice, guys, there's a pattern here. A sub 3 plus A sub 2. Now, what is the value of A sub 3? We just found it right here. It's 2. What's the value of A sub 2? They gave it to us. So 2 plus 1 gives us 3. So here's the fourth term, okay? So by relying on those previous terms, guys, to get to the next term, okay, we are using a recursive formula. One of the most common recursive formulas is the Fibonacci sequences, okay? Now, on this one right here, guys, let me go ahead and do this with you. Did we have A sub 5? Yeah, let's calculate A5. A5 is A sub 5 minus 2 plus A sub 5 minus 1, which essentially gives us A4 plus A2. Now, A4 is 3, A2 is 2, so when we add it up together, we get 5. Now, guys, can somebody find the next two terms? Let's find the next two terms. What would the next two terms be? Okay, now let's break it up. Let's break it down a little bit more. So if A sub 5 was the sum of the fourth term plus the third term, then A sub 6 would be the sum of the fifth term plus the fourth term. So the sum of the fourth and the fifth term. Now the fifth term is 5. The fourth term is 3. So when we add them together, we get 8. Okay, let's do one more and then we'll list it out. So the seventh term would consist of the value of the sixth term plus the value of the fifth term. So you would end up getting 8 plus 5, which is equal to 13. So guys, the Fibonacci sequence includes the first term, which is 1, the second term, which is also 1, that's given to you. Now the third term is based on the first term and the second term, so it's the sum of the first and the second, and then you go on from there. Now, the fourth term would represent the sum of the second term and the third term, and then the list keeps going on and on and on to infinity. Questions on this one, guys? Any questions? All right, guys. So now let's go ahead and talk about some of the properties and summation notation. Now, one of the ways, guys, for us to do these is to use the summation notation. Now, when we talk about the, oops, I went to the wrong thing. Okay. Summation notation. Now, what this allows us to do is to add or find the sum of the terms of a sequence, and then later on, it's a symbol, by the way, we're going to look at in a minute. Later on, we're also going to be talking about the series, but for now, guys, the summation notation allows us to find the sum of the terms of a sequence. The symbol we use for this is this. This is a Greek letter, and aka sigma. And so when we write these sequences using this notation, we could call it sigma notation, guys. All right. Now, for this sigma notation, typically it gives you a lower limit, We use K to indicate the lower limit. Let me write this down for you guys. Lower limit, as in the smallest value you're allowed to plug into this sequence, into this pattern. Remember, a pattern is just a function, okay? And then it's got the upper limit. The upper limit is the largest value you can plug into the sequence. And when you talk about the upper limit, most of the time it's infinite, so it goes up to infinity. And if they want it to be a finite, they would go ahead and plug in a number right here, guys. They would plug in a number for n over here. So rather than having an n for the upper limit, they would actually plug in a number. And then, guys, right here, you have your formula, okay? This is the formula or the pattern. All right, so for example, earlier we looked at this one right here. F of n is equal to 1 over n, all right? So let's say we wanted to do the summation notation for this one. It would be this. The lower limit would be 1, okay? The upper limit for this one would be n, okay? That's a k, guys. K equals to 1. And then the formula would be 1 over k. Now, k is the number that you're plugging into the formula. Could you go ahead and plug in n in here? Yeah, you can, but it really doesn't matter. So what this is saying is you got to find each term, find the value of each term, and add them up. So once again, find the value of each term and add them up. So for example, since we did this already, the first term was 1, the second term is 1/2, the third term was 1/3, the fourth term was 1/4, and it keeps going on and on and on. Now, the question is, where do you stop? They wanted you to go ahead and find the sum of all these numbers, but they didn't restrict it. They didn't tell you at what value you need to stop. So they need to have a number of terms they want you to go up to. So one of the ways this could be written is the summation, the sum of the first 5 terms. So k would equal to 1. And then the upper limit for this one, you might see something like this, 5. So they want you to calculate the first 5 terms of the sequence. So if they want you to calculate the first 5 terms, the first one would be 1. The second one would be 1/2. The third one would be 1/3. The next one would be 1/4. And then the next one after that would be 1/5. And then of course you would have to sit there and add them up together. When you add all of them up together, so the question is, what do you get for the sum of the first 5 terms of this sequence, guys? All right, somebody throw that on a calculator and add them all up together for me, please. Anybody? No, nobody got it? All right, so you would have to find the LCD between all of these numbers. What's the LCD between all of these denominators, guys? Anybody? No? Okay, 40 would be the LCD. So this one right here would become 40. This one right here would become 10. The next one would become, oh no, wait a minute, not 40. 3 doesn't go in for 40, Shazam. Ooh, I just erased the whole thing. Let me call it, there we go. Not 40. Let's try this again, 60. Let's try 60 instead. So the first one would be 60. The second one would be 30. The third one would be 20. So you guys notice a little pattern there? Then 15 and then 12. You would add it all up together and then divide it by 60 and reduce it. So what would it come out to, guys? Somebody throw that in a calculator. 137 over 60. Or you can change that to actually 2 and 17 over 60. Okay, 60, that's 60 right there. All right, now guys, let's get to some of the rules of summation notation. Now, for the properties, we're going to look at properties of sequences and the properties of the summation notation. So first and foremost, guys, sometimes when we talk about the summation notation, k equals to 1, and then of course this goes all the way up to n, as n it goes up to infinity. If you've got a value multiplying the k right here, that value, rather than having to multiply here by that value, that constant, you can factor it out, find the value of the summation notation, and then multiply everything by it. Oh, I forgot to mention this to you guys. This is also on your calculators. I'm gonna have to find it on your calculators since I don't have my graphing calculator with me. So I'll have to do it with you later on. Okay, guys. So bottom line, if you've got a constant multiplying the formula right here, that constant can be factored out and multiplied by the value of the sum notation of k. Now, let's move on. The next one, we've got this one right here, where you're adding 2 things, k1, and this goes all the way up to n, and let's say it is a sub k plus b sub k. Now, this one right here, you could break it up into 2 summation notation. So when you break it up, you have the sum of a sub k plus the summation notation of, okay, the b sub k. So in other words, you find the sum of each one, and just add them up together. Now, the next one, guys. For the next one, it is very similar to the previous one. The only difference is that, it's now a difference, okay? So if you have something like this where you have a sub k minus b sub k, you can break this up into the difference of the 2 summation notation, k1 to the n of a sub k minus, okay, the sum of the, let me see, up to n, and then the b sub k. So in other words, you can break this up, guys. You can separate them to calculate the values of each summation and then subtract them together. Now, the fourth one is where, let me see here. What was the first one I was going to tell you guys about? Okay, so here's the fourth one, guys. Now, for the fourth one, let's say, and this one is a little bit more complicated, okay? You have k equals to j plus 1. and then this goes all the way up to n, and then you have the formula a sub k here. So this one right here, guys, you can take it and break it up into this, okay, two parts, all right? Because you have j and you have 1. So you can break it up into two formulas, okay? K equals to 1 up to n. And then I am going to be doing examples with you guys in a minute, so just give me a moment. A k, and then minus, that's an n up here. It's a little broken off right there, okay? So when we do this part right here, guys, we're going to have k equals to 1 and then a sub k, but this one goes all the way up to n. Now that's a b, okay? So now, what in the world does this mean? What in the world is going on? All right, guys, so let me go ahead and show you, okay? I am going to start with some easy ones, okay? So here's an easy one. Let's say for this one right here, we have, hold on a second, looking for a very, very easy one. Ooh, that one is too hard. Okay. All right. You know what? Let me just go ahead and create one. Let's just create one. Okay, so here's one. K equals to 1. And then the formula for this one, guys, is a negative k. And this goes all the way up to 10. You have to calculate the value of this. There are two ways for you to calculate the value of this. What does k equals to in the last part? Ooh. 1. Okay, right there. Okay. Now, guys, there are two ways for you to do this. You can actually sit there and take the values. K equals to 1, plug it in, you get -1. K equals to 2, you plug it in, so you get -2. And you just keep adding the numbers like this, okay? Just keep adding the numbers until you get to the 10th one. The other option is to go ahead and do this. Because you have this negative leading coefficient right here, you can take out the negative leading coefficient and then break this up into k equals to 1 up to the 10th power and then k. So now, guys, when you're adding this, this is what you're going to be adding. You're going to be adding 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. You add all this up together, and then once you're done adding it up together, you put your negative as the coefficient, okay? Now, here's the big question for you guys. What is a quick way of adding up all these numbers instead of having to write down 1 plus 2 plus 3 plus 4 plus 5 and so forth and so forth and so on? Here's another way to do it, guys. All right? Now, pay attention to this one, okay? I am going to take the first element and add it to the second element. So I'm listing all the elements in this sequence. Well, you know what? Let me just go up to 5, okay? And then for the second line, I am counting backwards. I'm going backwards for the terms of the sequence. So the 10, the 9, and then the 8, okay? And then 7, and then 6. Now, guys, we're going to add them together. Let's see what happens. 1 plus 10 gives us 11. 3 plus 9 is also 11. 3 plus 8 is also 11. So what you should notice is that we are creating a whole bunch of pairs of 11s. How many pairs of 11s do we have? We have 5 of them. 5 times 11 is 55. And so this is a quick way for you to be able to add up a whole bunch of numbers together. Once you figure out the pattern, guys, that you're creating a whole bunch of pairs of 11, just count out how many pairs you have. So what did I do? I paired up the first number with the last one, the second number with the one next to the last one, the third number with the one that is 2 numbers previous to the last one. And what I'm doing is I'm creating a whole bunch of pairs of 11. So once I figure out how many pairs of 11s I have, I take that number and I multiply it by 11. Eventually, guys, that's going to lead us to another type of pattern But for now, just know this is what we're doing. So what's the outcome of this problem? Well, we just added all these numbers inside the parentheses. There was a negative out here. So the answer is going to turn out to just be negative 55. Now,
So,
go ahead.
for the fourth property, I didn't understand the second part when you put in segment of the,
Okay.
when you like factor it out, I didn't understand like the 0 TC, like what was that?
Oh, no. That's not 0 TC. That's supposed to be BK. Okay. That one's
Okay.
B sub K right there. Okay.
Okay.
All right, guys. So I need you guys to do me a favor because I need to expedite the process. So I need you guys to be able to use your calculators. All right.
I have a question.
Yes, go ahead. Where did the J?
Yeah, where did the J go?
Okay, the J part would represent the entire problem. So you have one function here and you're adding one to it. So when you break this up, you're going to break this up into two parts right there, okay, to make up for that J that is missing. Does that make sense? No? Okay. Let me see here. Did I write the J in there? No, I did not write the J in there. That's why you're asking that question. Hold up a second. The J is supposed to be right up here somewhere. And this one right here is supposed to be, that's why you guys are confused. This is not writing well. Okay, guys, there's an N right there. This is supposed to be an N. And this one right here is supposed to be a J, okay? Oops. I lost my page. Okay. Oh, ow. Okay, I just lost everything. Shazam. Okay. All right, guys. I don't know what happened and I cannot recall it. Ooh. Okay. Well, there's a little tech problem I need to work on. Okay. I just lost it. But anyways, Paige, the previous problem, the formula, the first summation notation goes up to the limit. The upper limit is N, and then the second one, the upper limit is J, okay? So there's an N up there and there's a J up there for the second one, all right?
Why is this?
Thank you.
Why is this subtract instead of adding?
Okay, because here, when you're looking at this one, you're adding the one. So to make up for the addition, you're going to subtract it because eventually you have to get back to the original problem. Remember, when you add a number and its opposite, it turns out to be zero. So in order to get back to the original problem, you have to break it up so that you can subtract something to get back to that J plus 1 value. Now, there are proofs for this. Okay? The problem is I won't have enough time to go through the proofs for it. Here's the bottom line, guys. When it comes to working on the summation notation, if you know how to work out the problem and come out with the correct solution, do not get caught up in the minutia of the formulas. Don't get caught up in those formulas, okay? Because the formulas have a tendency to be somewhat confusing, but the goal is to get to the solution. So the question is, can you get to the answer? All right. Now, the general formulas, it takes a while to get used to them. So make sure you're working out the problems to see if it makes sense. All right. So here's something else I wanted to mention to you guys. On your calculators, guys, I need you to go on your calculators right now for the summation notation. If you go into math, somebody who has a graphing calculator, go into math. I don't remember exactly where it is. If you go into math, I want you to move over to num, and then I want you to go ahead and scroll down. You know what? Let me check and see if it's in the textbook because I do not have my calculator here with me. No, it's not in the textbook, guys. Okay, it's not in the textbook. All right, tell me what you guys are seeing on math. Who's got a graphing calculator right now in front of them and willing to share their calculator screen? Anybody?
I do.
Under math next to 0? Okay, that was Sarah. Okay. Sarah, can you put up your calculator on your screen so everybody can see it for me, please? It doesn't show up under num. Okay.
It's under math, and then it's under math, and then if you scroll down, like it's the 10 after it's the 0.
So, okay. So you hit math and then scroll all the way down. Okay, and it'll give you option. Keep going down. Okay. All right, hit that one. Okay. All right, guys. So, who is that? Is that Sarah? Okay, Sarah has her summation notation looking like this. Okay. Can you, here, let me write it down for you guys on my screen too, so you can see it. So you got K equals to a box over here, and then you have a box up here, and there's another box over here. Now, if yours doesn't look like that, guys, then you're going to have to do something else. Like this last problem we just did, Sarah, okay, you're gonna go ahead and type it in for me. So on that last problem, the lower limit is 1, the upper limit is 10, and then the formula was negative K. So there you go, negative X. So if you're on the calculator, don't use the K, you can't use the K. So put negative X in there, and then hit enter, Sarah, and see if it gives you the answer. You see that, guys? Can you guys see Sarah's screen? I can't find it. Laura, are you on a graphing calculator?
Yeah, I'm on.
She has the
83 plus.
Oh, you have the older version. Now,
Yeah.
for the older version, do you see something under the math menu that says sum, Sarah? I mean, not Sarah, Laura. Scroll down through the math menu and see if you see it there.
No, I look under num.
You don't see anything like that?
No.
Okay. Do me a favor. Just play around with it for a little bit and see if you can find anything that mentions sum. It's under the math menu somewhere. I just don't recall where it is in the older graphing calculators. But for those of you with the new graphing calculators, you can actually do this on your graphing calculators. All right, guys. I am going to do a couple more with you, and then I am going to go ahead and move on. All right. So here's a second example, guys. And if you've got a graphing calculator, just go ahead and plug it in there. This one right here, it says the lower limit is 1. The upper limit is 16, all right? And then for this one, the formula is K squared plus 4. Now, guys, for this one right here, we're going to break it up into, let's see here, if you want to break it up, you don't have to break it up. If you've got a graphing calculator, you can plug this directly in. Now, if we're going to break it up without a graphing calculator, this is what you would break it up to. The lower limit for the first part of this, we're going to break this up into a sum. K equals to 1. The upper limit is 16, and you do K squared, okay? Now, plus the lower limit for the second one is 1. And the upper limit is 16. And so this one right here is just a constant. Quick question for you guys. What would this one simplify to? What would it simplify to? Anybody? What would this one simplify to? Right here. Here, let me use my pointer. Right there. What would this one simplify to? The summation notation of K equals to 1 up to 16 of 4. What would that one simplify to, guys? Anybody? Ooh, nobody. Come on, somebody. Okay, guys. So on this one right here, because we're going from K equals to 1 up to, I'm erasing it, K equals to 1 up to 16, it means that the 4 is being repeated how many times? 16 times. So On this one right here, all you would be doing is taking the 4 and multiplying it by 16, or 16 times 4. So in other words, it's 4 adding to itself 16 times. All right, now, how do we calculate this part right here? Here's how we calculate it, guys. We figure out the first term. What's the first term? We take 1, we plug it in here. 1 squared gives you 1. Figure out the last term. What's the last term? 16 squared. When you do 16 squared, what do you end up with? 16. And then you add them up together. What do you get? You get 17. So now the big question you have to ask yourself is this: how many pairs of 17s have I created? Hold on a second. I'm going to erase this and do this again. Once again, I am figuring out, guys, the first term. What's the first term? Okay, so the first term would be the lower limit plugged in to the formula, 1 squared, which gives me 1. And then I'm going to figure out the last term. What's the last term? The upper limit, which is 16, plugged into the formula. 16 squared gives me, what's 16 squared, guys? 256. Now, we're going to add them together. So what do we get? 257. So now the question is, how many pairs of 257s do we have? How many pairs, guys? From 1 up to 16, how many pairs would you create?
8.
8 pairs. So to get your answer for this part right here, you would have 8 times 257 plus this value down here, which is 4 times 16. And everybody can do this on a basic calculator. So grab your calculator, guys, throw it on your calculator. Let's see what you come up with. Go ahead, give it a try. What'd you guys get? Where did the 8 come from? All right, so here's how we get the 8 page. Remember, the lower limit is 1, the upper limit is 16, okay? We found the first term, we found the last term, okay? We got 1 for the first term, 256 for the second term. We add them together. So in other words, we're pairing up the first term and the last term together. So when we pair up the first term and the last term together, we're creating a whole bunch of pairs of 257. How do we figure out how many pairs of 257s we created? We go, the lower limit was 1, the upper limit is 16. So how many pairs of numbers can we create out of 16 numbers? That's the question. How many pairs of numbers can you create out of 16 numbers? That's it, okay? You can create 8 pairs out of 16 numbers. So you take that 8 and you multiply. All right, so did you guys get the number? What'd you guys get?
I got 2,000 something.
2,000 something?
Yeah.
All right. Where did you add the 4 and the 16?
What 4 and 6? The other part?
Mm-hmm.
When I multiply by the 8, I got 2,056 plus 64.
2,056 plus what? 64?
Plus
Okay.
64.
That sounds about right. And then add them up together.
It gave me 2,120, but on the calculator it says 1,056.
1,056.
1,560 on the calculator.
1,560 on the calculator?
Yeah, that's why I was like, what?
Hmm. $1,000. What did you get on your calculator, Sarah?
I got 1,560 on my calculator.
What did you get?
I got 1,560. Yeah.
1,560?
Yes.
Ooh, what did I leave out? Oh, wait a minute. I went too far. Okay, let me see here. 1 plus the 256, and then k squared, 16 squared. Okay.
Oh, they're not the same value. It's not the same value.
What happened?
When 2 squared plus 15 squared does not give you 257, it gives you 229. It's different values each time.
229 for what?
2 squared plus 15 squared. Instead of, I went on with it and I got a different number.
You wrote out the terms of the sequence as in 1 plus 4, and then 4 plus, let's see here, 4 plus 4 and so forth and so on.
I wrote it like, you know how you did like 1 squared plus 16 squared? I did the continuous pair, 2 squared plus 15 squared, and that gave me 229.
229.
So
Yeah.
it's not 200.
No, it's not a continuous one.
Yes, it's not all of them are continuous.
Okay, I wonder what happened with this one right here. Probably because it's a square one. All right, so then let's go ahead and try this a little differently. Let's see what happens. Let me go ahead and clear it out. Okay, so if you do 1 squared and then 16 squared, 2 squared and 15 squared, 3 squared and 14 squared, let's see what it comes out to. This one right here is going to be 257. And then 2 squared is 4. 15 squared is 225. When you add that, you get 229. You're right. It's not coming out to be an exact value. 3 squared is 9. 14 squared is 196. And when you add those two together, that's going to be 205. It's not consistent. Why aren't we getting a consistent value for this one right here, I wonder? Okay. All right, guys. So pretty much on this one right here, we're going up to 16, right? K squared and then plus 4. There's your problem. Now, when you add this one up together, let's say you throw it on the calculator, the bottom value, you got to plug in the 1, and then the top value, plug in 16. So when you plug it in, make sure you type in the k squared plus 4 when you type in the value. Actually, x. Use an x in there, okay? When you guys type it in like that, what do you get? Do you get the exact same value on the calculator? What'd you guys get on the calculator when you typed it in like that?
With the k or with the x?
With the x. You could use k or x. It's easier to use x because the x is given to you right there. Okay?
1560.
1560. All right. So apparently the shortcut didn't work for that one. The question is, why didn't the shortcut work for that one? But guys, let me just say this. Because we can still pair up the numbers, you can actually continue this up to the 8 pairs of numbers in order to come up with the values by pairing this up. Now, the question is, and I am going to look at this one right here to see why it didn't come out, okay, is to go back and figure out why it did not work where when you add up the pairs, you get the exact same value again and again. And I think because this one right here is a geometric pattern, it's not an arithmetic sequence, but this is supposed to work for the arithmetic as well as the geometric ones too. So let's go ahead and give another one of these a try, guys, and let's see if we could get an answer using the same type of pattern. Let's try this one right here. Now, for this one right here, this is what I have. I have, this one's too easy, guys. Let's try this one instead. Okay, k equals to 1, okay? And I'm gonna try that summation notation again, all right? And this goes up to the 20th power, and this is 5k plus 3. Okay? So let's give this one a try. Let's see if we can come up with the answer without using a calculator, all right? So we're gonna break this up, guys. So when we break it up, we're gonna break it up in two, okay? K equals to 1, and then because this 5K right here is a coefficient times the value K, I'm gonna drop the 5 in front of the summation notation, keep my K right here, and all this goes up to 20, plus the sum of the summation notation of K equals to 1 up to 20 times 3. Now, obviously, this part right here is going to be 20 times 3, which gives us 60. Now, we're going to give this one a try right here, guys. So we're going to go ahead and add the first number and the last number together. So the first number would be 1, okay? And the second number, the second number would be 2. The third number would be 3. Now, if we're looking at the last number is 20. The one next to it is 19. The one next to it would be 18. When you add them up together, it does add up to a pair of 21. Since we're going from 1 up to 20, we would create 10 pairs of 21, guys. 10 pairs of 21. So here you would do 10 times 21, okay? And then add all of this to it. So 10 times 21 gives you 210. And then you're going to multiply this by 5 plus 60. So 5 times 210 is going to give you 1,050. And then plus the 60, guys. So this one should be 1,110. Did you guys get that for it? Did you guys get that one? Okay, nobody got that one. Talk to me, guys. Anybody got it? Okay, Sarah got it. Did you do it without your calculator, Sarah? Okay, Lee got it. Did you do it without your calculator, Lee? All right, good, good, good. All right, so now try it on the calculator and see if you get the correct answer for this one, guys. Try it on your calculator. In the meantime, I'm gonna try this cubic one. Let's see what happens with this cubic one. Okay, here's the next one. K equals to 5. Now be careful with this one. Leslie, you sound like you have a question, but you're not asking a question.
Yeah, it's 10:10. Are we almost done?
It's 10 till.
10:10.
Oh, it's 10:10. Ooh, okay. All right, yeah. Let me see here. I guess, you know what? I'll mention just a couple more things and then we'll go ahead and finish up, okay? All right, guys. So let's give this one a try right here. Now, this one, notice the lower limit is 5, guys. Okay. The lower limit is 5. So this one, we're going to have to approach it a little differently, right? So when you do this one, it's going to be 5 to the third plus 6 to the third plus 7 to the third, and so forth and so on, all the way up to 20 to the third. Now, if we were to go ahead and work this up, 5 to the third comes out to 125. 6 to the third comes out to 216. Now, somebody do 20 to the third, please. 20 to the third power. Tell me what value that comes out to. This is definitely going to be a calculator one because that's a large value here. Anybody? That's going to be 8,000.
8,000.
Mm-hmm. And then do 19 to the third for me, please.
6,859.
859. Okay, let's add these two together. So that would be 8125. Add the 216 and the 6859. Let's see what we get. Well, that's not going to work out.
7,075.
7,075. So yeah, the pattern doesn't hold true, guys. when it's a cubic or a quad. So this one, you're actually going to have to work it out. Now, here's the big question, guys. How many pairs of numbers would we end up with if we were to do this? Not 10. Why wouldn't it be 10?
Wait. Oh, because it starts at 5.
Mm-hmm.
So you just subtract 5 from the 20 would give you 15. You have one extra pair. One individual number by itself.
Okay. So let's do a quick count out, okay? If we're to count it out, you do 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. How many pairs would that be, guys? Okay.
It'll be 7 pairs and 1 number addition.
Yeah, so this one would be 7 pairs and 1 number extra. So you actually have to work this one out, okay? And plus, the pairs really don't matter that much. Why? Because they're not adding up to the same thing. However, here's what you do. I would go ahead and do 7 cubed plus the 8 cubed plus the 9 cubed and add it to the 18 cubed, add it to the 17 cubed if you're doing this on paper. But guys, you're doing this on a calculator, so you would go ahead and throw it on your calculator. Now, if you're on your graphing calculator, the lower value is 5. Be careful with this. The lower value is 5. The upper value is 20. When you go and plug it into the formula would be x to the 3rd, and then you hit your equal sign. This one is going to be an exorbitantly large number. Somebody plug that into a calculator, please. Tell me what you come up with.
It's 44,000.
44,000 exactly?
Yes.
All right. And so, guys, here's the bottom line to this. First, they give you the little formulas, okay? They're going to ask you to find a specific number of terms, okay? So that's one. You have to be able to, here's a formula, find, let's say, the first 5 terms or the first 6 terms, okay? So that's number 1. Number 2, here is the first term, the second term. Now, figure out maybe 4 additional terms or 5 additional terms, which is very similar to the first one, except now they give you the first term and they give you the second term, okay? So we're looking at those recursive patterns, all right? And then thirdly, the summation notation helps you add up all the terms in a sequence, guys, all right? So they give you the summation notation formula. Once you have the formula, they give you a lower limit, upper limit, okay? And then you figure out the terms one at a time and then add them up together so you can find the sum of the entire sequence. Now, as we move forward, guys, we're going to keep seeing the same thing over and over again. The same variables, the same summation notation, whether we're talking about the arithmetic sequence and series or we're talking about the geometric series. We are going to be using the same types of variables and the same types of notation with these problems. Now, before I let you guys go, I'm just going to say one last thing and then I'll let you guys go. And that is the arithmetic sequences, which I alluded to earlier. Now, for the arithmetic sequences, these are, again, patterns where each term is found by adding, and remember I told you guys this earlier, or subtracting the same value from the previous term to get the next term. Now, guys, remember these are still functions, okay? So here's a quick example. Let's say I have this sequence right here. Let me use a different number here, okay? I have 4, and then I have 10, and then I have 16, then I have 22, and so forth and so on. Now, when you are given these arithmetic sequences, how do I plug the problem into the calculator? Okay, hold on, Stacy, stay with me after class and I'll show you. Okay, so guys, look up. So the first thing you have to do is to figure out the pattern. Now, for the pattern, that number that you keep adding over and over again to get to the next term is called the common difference. So looking at this sequence right here, guys, what would be the common difference? What is that value that keeps adding, that they keep adding to each term to get to the next one? What do you notice?
6.
That one is 6. So your common difference, okay, that number that you keep adding over and over again to get to the next term is 6. Now, once you figure out the common difference, they may ask you to find the next 2 terms. Find the next 2 terms. Now, to find the next 2 terms, since you know what the pattern is, what the common difference is, what you do is you add the 6 to get to the next term, which gives you 28. Add the 6 to get to the next term, which gives you 34, okay? So these type of patterns, guys, where you're adding or subtracting the same number over and over again, is called the arithmetic sequences, okay? So before we're just talking about sequences, could be any type of sequence. They could have patterns, they may not have patterns, and if they have a pattern, the pattern could be geometric, multiplications and division, or it could be arithmetic, subtraction and addition. But here, we're specifying them. This is an arithmetic sequence. This only has to do with addition and subtraction. Now, last thing I want to say is the nth term, finding the nth term of an arithmetic sequence. So when they want you to find the nth term of an arithmetic sequence, we call this the general term formula. The formula is this. It is a sub n equals to a1 times, plus n minus 1 times d. Again, guys, what you will notice is that we have the same variables. Remember, this is a function all over again. The only difference is that we have a d here. The d represents that number, the common difference that you keep adding or subtracting from each term to get to the next one, okay? So a1 is your first term, remember that. And then n, of course, is the term number. So wherever you find a n value, you go ahead and plug in the term number, all right? So guys, that last sequence we're just looking at, 4, 6, 16, the next one was 22, and so forth and so on. If they were to ask you to find the 50th term in the sequence, they wanted you to find the 50th term in the sequence, okay? Rather than having to sit here and listing out all the terms in order to get to the 50th one, then you go back into the formula, you plug it into the formula, okay? So what do we have? We have the first term, a1 is equal to 4. We have the common difference. The common difference is 6. And we have the term we're looking for in this case, which is 50. So we go into the formula, a sub 50, as in the 50th term in the sequence, the 50th term in the sequence will equal to the first term, which is 4, plus the term number minus 1 times the common difference, which is 6. And of course, you have your graphing calculators, or any calculator for that matter. You take your calculator and you plug this into the calculator and let the calculator figure it out for you. Somebody quickly plug that into the calculator for me, please.
It's 298.
It's 298. Ooh, let me write it down here. 298. Now, how do you guys feel about that one? You comfortable with it? Anybody? No questions? Okay, I'm seeing 2 thumbs up, maybe 3. Okay, there's a couple more. All right, guys. So If you're comfortable with this part, I could leave it. You know what? I feel like we need to do a summation notation. Okay, let me see. Okay, guys, let's try this one right here. For this one right here, this is gonna be our last problem, okay? Last problem. Find the, and I'm not done with this section right here. This is 12.2, by the way. All right, find the 80th term given 5, 0, -5 represents the first few terms of a sequence. Find the 80th term, okay? So guys, remember we're using the formula AN is equal to A1 plus N minus 1 times D. Okay, so the first question is, what's the first term? What's the first term? 5. And then the next question is, what is the common difference? What is the term that we keep adding over and over again to get to the next one? -5. Very good. So guys, you want to make sure you be careful with the negative, all right? So we have the first term. We have the common difference, which is -5. The term we're looking for is the 80th term. Now, let's find the value of the 80th term. So A sub 80 will equal to the first term, which is 5, plus the 80th term minus 1 times the common difference of -5. You guys go ahead and plug that into your calculator. Just a couple of reminders, guys. Number one, we are not going to be taking a test on this part right here. However, you will have some of these questions appear on the final exam, okay? So you need to know how to do them. -400 plus 5. Okay, so did you guys get -390? You got 400. Okay. Okay, I see you, Laura. Okay, guys. So yes, we're not testing on this. We're trying to get up to lesson 12.5 this week. And then next week, we're going to touch up on the not ellipses, the conic section. And the conic section includes the quadratics. It includes the hyperbolas, the ellipses, the circles. Obviously, we've talked about the parabolas and the circles before. So the focus will be on the ellipses and the hyperbolas. All right. Now, in terms of the assignment, guys, there are 3 assignments for chapter 12, 1 assignment for chapter 10. And so start working on them, okay? See how far you can get. On Wednesday, we'll finish up section 12.2 and move on to 12.3 and 12.4. On Friday, I'm hoping to get to the binomial expansion. Now, what in the heck is a binomial expansion? Here it is, guys. If you're given a problem like this, x plus 4 to the, let's do this, to the 7th power. You have to sit there and expand it. When you expand this one, you will end up with 8 terms. So what are those 8 terms? In other words, if you multiply x plus 4 times x plus 4 times x plus 4 7 times, what would the answer be? Those are the binomial expansion problems, which we'll be talking about on Friday. All right. So I'm going to end here, okay? Do you guys have any questions?